In this video, we'll continue our discussion of section 2.6 part 1 by defining a new way to determine if a DE is homogeneous polar. I gave you the first definition of putting it in terms of y over x. I think that's more work than it's worth. I think these are much better ways to work it out. So that is a way to do it. I would encourage you to try it. And if you'd like to see an example, I can find one in the solution manual that works out that way. This other way I think is much easier and quicker. If a DE can be written in this form, so if I can get dy over dx equals some fraction, then if this fraction is homogeneous function, if that function is a homogeneous function of degree n, and this function is homogeneous function of the same degree, then the DE itself is homogeneous polar, and then we can use the methods I'm about to show you. But we have to show that first. Now, sometimes the DE is written in this form, and it's the same thing. If these two functions, m and n, the ones in front of dx and dy, if those two functions are homogeneous functions of the same degree, then the DE itself is a homogeneous polar DE, and we can use the following method. Now, what I do here, if you would like to, I don't start, if I start here, then I actually move pretty quickly to y equals vx. That's how I think about it, just so you know. Write that in. Check out this after we're done doing the next example. I don't like to read off the steps without working the example first because you're just going to zone out while I do that. All right, so this first one, what I like to do, if I can, and it's easy, is I like to get dy dx by itself. And I'm going to show you the other method so you don't have to in the next example. So I'm going to work on getting dy over dx. So I'm going to add x squared dy to the other side. So I got 4x squared plus xy plus y squared dx, and then I add it over, I get x squared dy. All right, now I have functions I try to get dy dx, so I'm going to divide both sides by dx and divide both sides by x squared. So I got dy over dx, and then I got x squared over x squared, 4x squared plus xy plus y squared. Okay, so now I put it in that form, and you'll see why here in a moment. I need to, before I even try to move forward with this method, I have to make sure that it's going to work out. So I guess they didn't call it m when we had it in this form. They called it f, so I'll do that. F of xy is the top function. So f of tx ty is equal to, this one's really easy to see, t squared times x squared. This is homogeneous, draw an arrow, homogeneous degree 2. I also have gxy, which is that below function, the denominator at 4x squared plus xy plus y squared. Right? I'm going to plug everything in there. Tx squared plus tx times ty plus ty squared. I can see everything's going to have a t squared, so I'm just going to do this. T squared times gxy. This tells me it is also homogeneous degree 2. Since I have both of those, this tells me by what we just read that the DE is homogeneous polar. So we can continue with the method I'm about to show you. Okay, so we're going to start off. I have that D. I'm going to write it again, so I have it down here now to keep scrolling back up. Equals x squared. I'm going to keep it in this form. And I'm going to make a substitution. The substitution I'm going to make is I'm going to let y equal v times x. I'm trying to come up with a solution for this. So that's going to be my solution. I'm going to try to find v, work it out. Once I get v, I can find y. So when I take my derivative here, and remember, this comes from this definition. You can see you can manipulate that equation to get that. I can use this to take my derivative of that equation with respect to x. So that's my left side, dy dx. Now, when I take my derivative, I get v plus, okay, and it's a product rule. So I took derivative of x, that's 1, and then I get v. Plus, the derivative of v is 1 times x, and then I don't know what v is, so I need to make sure that's implicit differentiation back from Calc 1, that also holds true. So now what I do, if you notice, I have that equation above. I can just replace the left side with this. So I get v plus x times dv dx equals, and then I replace anything that has an x squared in it, we replace. I think I have this thing flipped, if I'm not mistaken. Let's see. Yeah, this thing should be flipped. Some of you guys probably noticed that already. I'm not going to re-record. I'm just going to move this. It's much easier. I apologize. Please fix your notes. Then we have this. I'm going to erase that. The good thing is we haven't started. I just noticed it wasn't going to work out. All right, there we go. Everything still applies. It's the same thing. All right, so I then now have, I'm going to erase that fraction bar. We have 4x squared, and everywhere there's a y, I'm going to replace it with vx. Okay, I want you to notice everything has an x in it. So I get v plus x times dv dx equals, everything has an x squared, so I'm going to divide everything. 4 plus I get v plus I get v squared. Now I want you to notice something here. There's a v on both sides. So I get x dv dx equals 4 plus v squared. The reason we do this substitution is this is separable, right? The whole point, we talked about this in that beginning video. We're going to do a whole lot of like, here's a method. Once we do this method, it's going to turn into this kind of differential equation, which we know how to solve, just like we solved normal equations back in algebra. So notice it's separable, so I need to move things around. I got 1 over, I'm going to rewrite this real quick, 2 plus v squared, and that's going to make sense here in a moment. We divide by x for this side, and we get our dx. So we have that. Now, we have the integral of 1 over 2 squared plus v squared dv, and the integral of 1 over x dx. The right side, I hope you're getting used to that, shows up a whole lot. I have that. I'm going to call it C1 because we're going to change it here in a moment. Now, this from a table, I would get this memorized. 1 over that is arctan. And it's always 1 over a, whatever that is, and then it's 1 over a variable there. This one shows up a whole lot as well. So I would get that thing memorized. Now, there's not a whole lot we can do from there. I can multiply by 2, so let's do that. Arctan. And I'm going to go ahead and change this 1/2. I know v is y over x, so I'm going to make that replacement. And then I got 2 times ln of x. And I'm just going to write c now because it's 2 times c1. But I don't need to write 2 times c1 because that's just another constant. Solving for this, we totally could. It's actually not that bad. You take a tangent of both sides, you multiply by 2, and you multiply by x. But we are going to stop there. All right, that is a fantastic answer. We want to stop because it's nice and pretty. There's no reason. We have a function. There are no derivatives. We could solve for y if we wanted to. That is how you solve a homogeneous polar differential equation. Have to show that they're both, get it in the right form, show that they're both homogeneous functions, right? That tells me the DE is homogeneous polar. Then I use this method, y equals Vx.